For decades, we believed we had a clear timeline for the universe, a slow, orderly story of stars, galaxies, and cosmic structure unfolding across 13.8 billion years. But when the James Webb Space Telescope looked deeper into the early universe than ever before, it found something far stranger: galaxies that seemed too bright, too massive, and too mature to exist so soon after the beginning. If these discoveries are correct, then we may not just be looking at the edge of the observable universe, we may be looking at the edge of our understanding. Before we begin, thank you for being here and spending this time with us. If you enjoy calm, thought-provoking journeys into the mysteries of space and science, please like the video, subscribe to the channel, and share it with someone who loves the universe as much as you do. And one more thing, we'd love to hear from you. What time is it where you are, and where in the world are you listening from? Please leave a comment below and say hello. Now, let's begin. Long before the James Webb Space Telescope began returning its deep infrared images, the modern story of the universe already seemed remarkably complete. It was not complete in the sense of knowing everything, but complete enough to feel internally stable, a structure built from many lines of evidence that appeared to reinforce one another. At the foundation of that structure lay a faint radiation spread across the sky, the cooled afterglow of the early universe, known as the cosmic microwave background. It carried the memory of a time when matter and light first moved freely through space, leaving behind a textured pattern of slightly warmer and slightly cooler regions. Those small variations mattered because they were understood as the first unevenness from which later structure would grow. From that ancient signal, together with the motions of galaxies, the behavior of gravity across immense distances, and the measured abundance of the lightest elements, cosmologists assembled a narrative of striking coherence. The universe begins hot and dense, expands and cools, and over immense spans of time matter gradually gathers into stars, galaxies, clusters, and the vast cosmic web. For many years, this picture did not feel fragile. It felt disciplined, tested, and broad enough to hold the visible history of everything. Within that framework, the standard cosmological model, often described as lambda CDM, became the working blueprint for how the large-scale universe evolves. Its central claim was not that ordinary matter alone built the cosmos, but that most of the gravitational scaffolding came from dark matter, an invisible component detected not by light, but by influence. Dark matter was thought to collapse first into halos, broad gravitational wells that gave ordinary gas a place to fall. Inside those halos, hydrogen and helium slowly thickened, cooled, and under the right conditions ignited into the first stars. Over time, those stars lit the first galaxies, and those galaxies merged into larger systems. The model also included dark energy, represented by the lambda term, to account for the accelerating expansion of the universe on the larger scales. Together, these ingredients formed an elegant compromise between what could be directly observed and what had to be inferred from motion, timing, temperature, and structure. What made the model powerful was not only its ambition, but its success. It explained why the universe looked clumpy instead of smooth. It explained why galaxy clusters held together. It explained why the oldest light carried the particular statistical pattern that telescopes recorded. It did not answer every question, but it provided a convincing timetable. That timetable mattered deeply. In the accepted version of cosmic history, the earliest phases after the Big Bang were energetic but simple in their large-scale architecture. Matter did not leap instantly into grand mature systems. Gravity needed time. After the primordial plasma cooled and neutral atoms formed, the universe entered a long interval in which no stars yet shone. This era is sometimes called the Cosmic Dark Ages, though the term does not mean chaos or menace. It simply marks a period before the first stellar light. Eventually, in the densest pockets of dark matter halos, gas began to collapse further, and the first stars ignited. The radiation started to alter the surrounding hydrogen fog, gradually transforming the young universe from opaque to transparent across great distances. This process, known as reionization, was not thought to happen all at once. It unfolded in patches as more stars and small galaxies appeared, each contributing to a slow clearing of the cosmic haze. In this picture, the first galaxies were modest objects, dim compared with the giant spirals and ellipticals of the later universe. They were expected to be chemically primitive, structurally irregular, and limited in mass because there had simply not been enough time for repeated cycles of star formation, stellar death, enrichment, and merger-driven growth to produce anything much larger. From this gradual view followed a broader expectation about how the universe should look when observed at great distances. Because light takes time to travel, the deeper a telescope peers into space, the farther back along cosmic history it sees. A galaxy observed from a very early era is not being viewed as it is now, but as it was when the light began its journey. This principle had already transformed astronomy into a form of historical reconstruction, yet the reconstruction came with a hidden assumption. If the standard model was broadly right, then looking farther back should reveal a simpler universe. The earlier the epoch, the fewer opportunities matter should have had to organize itself into large, luminous, chemically evolved systems. One expected a kind of youthfulness in the distant cosmos, not in any sentimental sense, but in the physical meaning of incompletion. Small galaxies should dominate. Star formation should be underway but not yet layered by long history. Heavy elements such as carbon, oxygen, and iron should be rarer, because they are forged inside stars and dispersed only after those stars live and die. Large black holes might exist in seed form, but the most enormous galactic structures should still lie in the future. The universe, in that view, grew up slowly. This expectation was not invented from preference. It arose from decades of increasingly refined observation. Telescopes on the ground and in space, especially the Hubble Space Telescope, had already pushed human sight deep into cosmic time. Hubble revealed galaxies from earlier and earlier epochs and showed that the distant universe was real, populated, and active. It revolutionized the field not by overturning cosmology, but by giving the standard story visual depth. Its famous deep fields exposed thousands of galaxies in what once looked like empty darkness, demonstrating that the sky was crowded even where the eye saw nothing. But Hubble also had limitations that were well understood. As the universe expands, light travelling across it is stretched toward longer wavelengths. The farther the source, the stronger this redshift becomes. For the most ancient galaxies, light that began in the ultraviolet or visible range arrives in the infrared. Hubble could detect part of that shift, but not all of it. There came a point beyond which the earliest light was moving out of its most sensitive reach, so the image of the infant cosmos, though profound, remained partial. It suggested a young universe filled with faint, compact beginnings, but it did so through a window that scientists knew was incomplete. Even so, before Webb, the incompleteness did not appear catastrophic. It looked manageable. The sort of missing detail that a more powerful telescope would clarify without changing the underlying plot. The expectation was not that the first chapters of cosmic history were wrong in spirit, but that they were blurred at the edges. Better infrared vision would find earlier galaxies, measure them more precisely, and help confirm how the first structures assembled inside dark matter halos. It might refine the timing of reionization, improve estimates of early star formation, and perhaps reveal surprising objects at the margins, but the broad rhythm still seems secure: small before large, simple before complex, slow accumulation before grand maturity. The Milky Way and galaxies like it were understood as late achievements, shaped by long histories of merger, accretion, and internal change. The young universe, by contrast, was expected to be a place of tentative beginnings. That belief rested not on a single result, but on an entire architecture of connected reasoning, one in which each observation seemed to strengthen the next. This is what made the moment before Webb so important. Cosmology was not entering a void of ignorance. It was standing on a carefully built platform, stable enough that many of its practitioners expected extension rather than disruption. The questions were real, but they were bounded. How early did the first stars ignite? How quickly did the hydrogen fog clear? How fast could the first black holes grow? How soon did galaxies begin to cluster? These were not small questions, yet they lived inside a larger confidence that the universe had unfolded according to a comprehensible sequence. The deep past might still hold surprises, but the machinery guiding it seemed known in outline. In that sense, the pre-Webb cosmos was not mysterious because it lacked a map. It was mysterious because the map reached almost to the beginning and still felt readable. What remained was to push the line of sight closer to the first light and see whether the earliest pages matched the theory that had been written from afar. The next step was not to invent a new universe, but to look at the old one with sharper eyes and discover whether its youth had truly been as spare, gradual, and orderly as the blueprint implied. Every photon crossing deep space arrives altered. Light does not move through an unchanging stage, but through a universe whose fabric has been stretching ever since the hot beginning, and that expansion leaves a visible signature on everything that travels long enough within it. A wave of light that begins its journey sharp and energetic can arrive broader, longer, and redder than when it was emitted, not because the source itself has aged in transit, but because the space between galaxies has expanded while the light was on its way. This is cosmological redshift, one of the most important ideas in all of modern astronomy, because it turns the universe into both a physical landscape and a historical record. The more strongly a distant galaxy's light has been stretched, the farther it has travelled, and the farther back in time that galaxy is being seen. In this sense, distance and antiquity become entangled. A telescope pointed deeply enough into space is no longer merely collecting remote light. It is collecting earlier light, preserving an older state of the cosmos inside every faint signal it can separate from darkness. NASA explains this directly in its Web Science materials. The expansion of the universe stretches travelling light to longer wavelengths, and the first, most distant galaxies must therefore be observed with infrared detectors rather than with instruments limited mainly to visible light. This principle had been understood long before Webb launched, and it shaped the telescope's purpose from the beginning. Hubble had already shown how powerful a space observatory could be when placed above Earth's atmosphere, revealing galaxies across a huge range of cosmic history and demonstrating that even tiny, apparently empty regions of sky contain astonishing numbers of distant systems. Yet Hubble's great strength was not identical to Webb's. Hubble works primarily in ultraviolet, visible, and a smaller portion of the near-infrared range. That made it a superb instrument for many problems, from nearby star formation to distant galaxy surveys. But the deepest reaches of the early universe were always drifting toward wavelengths beyond its best view as redshift increased. Webb was designed specifically for that missing regime. NASA's wavelength comparisons show that Webb reaches far deeper into the infrared than Hubble, extending from the red edge of visible light well through near-infrared and into mid-infrared territory, which is precisely where ancient light from the earliest galaxies is expected to arrive after crossing expanding space for billions of years. That distinction matters because the first chapter of cosmic history is not hidden behind ordinary distance alone. It is hidden behind transformation. A young galaxy may once have shone intensely in ultraviolet light from hot newborn stars, but by the time that radiation reaches present-day instruments, it can be shifted so far toward longer wavelengths that a telescope built for visible astronomy would miss much of it, or fail to characterize it clearly. Webb does not defeat cosmic distance. It meets distance on the terms that cosmic expansion imposes. That is why it is often described as a machine for seeing the early universe, though even that phrase is slightly incomplete. What Webb really does is recover ancient light after that light has been stretched, diluted, and displaced from the domain where earlier observatories were most effective. It is an observatory built not just for faintness, but for altered faintness. To do that work well, the telescope has to remain extraordinarily cold, because infrared astronomy is a battle against heat as much as darkness. Warm objects glow in infrared light. A telescope that is too warm begins to contaminate its own measurements, raising an internal fog that interferes with the delicate signals arriving from remote galaxies. Webb avoids that problem through a combination of design choices that are easy to describe and difficult to achieve: a large segmented mirror for gathering weak light, a multi-layer sun shield the size of a tennis court to block sunlight and maintain deep cold, and an operating position far from Earth where the observatory can remain stable while keeping Sun, Earth, and Moon on the same general side of the shield. The telescope resides near the second Sun-Earth Lagrange point, roughly 1 million miles from Earth, a gravitationally useful region that helps it maintain this thermal geometry. These engineering choices are not incidental background. They are the reason Webb can function as a detector of ancient infrared light at all. Without cold stability, the earliest universe would remain partly buried beneath the telescope's own heat. NASA describes Webb's mission in exactly these terms: a premier observatory built to probe the mysterious structures and origins of the universe, using instruments optimized for infrared observation that can reveal objects hidden from visible light surveys. Once that physical logic is understood, the time machine comparison becomes less metaphorical and more exact. Looking outward always means looking backward, but the degree of backwardness depends on the wavelength the telescope can actually capture. A nearby star may appear close to the present because its light has not travelled long. A distant galaxy cluster may appear as it was when much of Earth's present biological history had not yet unfolded. A very ancient galaxy, seen near the frontier of Webb's reach, appears from a time when the universe itself was young, dense in hydrogen fog, and only beginning to organize starlight into the structures that would later seed the cosmic web. In practice, this means that a Webb image is not simply a deeper version of a Hubble image. It is often a different historical slice of reality. The same sky can contain layers of time superimposed in one-field foreground stars from the Milky Way, intermediate galaxies from much later epochs, and faint red systems whose light began its journey when the universe was still in its opening span. Webb's first deep field made this power visible immediately. NASA's release of the image of the galaxy cluster, SMACS 0723, described thousands of galaxies filling a patch of sky as small as a grain of sand held at arm's length. With some of the magnified background systems seen from when the universe was less than 1 billion years old, the image was not important only because it was beautiful. It demonstrated that infrared depth could draw distant galaxies into much sharper historical focus, and do so in exposures that pushed beyond the infrared depth of Hubble's deepest fields. Yet the deeper meaning of Webb's infrared view lies not only in how far it reaches, but in what kinds of questions that reach makes possible. Earlier telescopes could suggest that the young universe contained faint galaxies. Webb can push closer to asking what those galaxies were actually like. Were they chemically pristine or already altered by previous generations of stars? Were they compact and tentative or unexpectedly structured? Were they isolated or already participating in the mergers and interactions that later shape mature galactic systems? The telescope's instruments allow astronomers not only to image these faint sources, but also to spread their light into spectra, separating wavelengths so that redshift, composition, and physical conditions can be inferred from patterns in the signal. NASA's descriptions of Webb's spectroscopic capabilities emphasize exactly this point. The shifted positions of recognizable features in distant galaxy spectra reveal how long ago their light was emitted, while the structure of those spectra helps researchers estimate mass, age, composition, and history. This is where infrared observation becomes more than a way to see farther. It becomes a way to convert ancient light into evidence. Every early galaxy Webb detects is not just another point on a distance scale. It is a test of the timetable built in the era before Webb. If the first galaxies are where theory expected them to be, then infrared astronomy confirms the outline of gradual structure formation. If they are brighter, heavier, chemically richer, or more numerous than predicted, then the fault does not lie in the fact that Webb looked deeper. The fault lies in the assumptions those deeper observations are now able to examine. That is why the telescope's infrared vision carries such unusual scientific weight. It does not merely extend an existing map. It reaches the place where the map was drawn from indirect reasoning and begins checking the earliest landmarks one by one. The older image of the infant universe depended in part on the limits of what could be seen. Webb changes that not by inventing new light, but by recovering light that was always on its way, stretched beyond the reach of earlier instruments and waiting for a telescope designed to meet it in the infrared. Once that hidden ancient light begins to arrive in usable detail, the early universe stops being a blank prelude and becomes a crowded historical scene, full of objects whose existence can either strengthen the standard narrative or force it into revision. The mechanics of redshift, cooling, wavelength, and instrument design therefore lead to a much larger consequence. Webb is not only looking farther into space than Hubble could, it is looking into an older and less forgiven version of cosmic history, where the universe has less time available for complexity and where every unexpectedly mature object places a sharper demand on theory. By opening that infrared window, the telescope does not simply brighten the distant past. It exposes how much of the past had remained invisible and how quickly the hidden parts of that past might begin to change. The story that seemed so stable before the first photons reached Webb's mirror. The first shock didn't come from a single bizarre object. It came from abundance. When Webb opened its deep infrared view onto regions of sky that had already been studied for years, the darkness did not merely become clearer, it became crowded. One of the most famous early images centered on the galaxy cluster known as SMACS 0723, seemed at first glance to be a brilliant portrait of one foreground cluster and the warped arcs of light behind it. But the deeper significance of the field lay in how much history had been packed into such a small patch of sky. Thousands of galaxies appeared there, layered across different eras of cosmic time, many of them so faint and distant that their light had begun travelling when the universe was still in its first long stretch of development. The image itself was not proof that cosmology had failed. Hubble had already taught astronomy that apparently empty sky is never truly empty. Yet Webb changed the density of that lesson. It showed that once infrared sensitivity was pushed far enough, the young universe did not look like a sparse scattering of first attempts. It looked active, populated, and in some places unexpectedly rich. That difference mattered because number counts are not decorative details. They are one of the simplest and most demanding tests of any model of cosmic evolution. A theory may permit a rare oddity without losing its balance. it is much harder for a theory to absorb a pattern in which the early universe contains many more detectable galaxies than anticipated. The standard picture before Webb allowed for early galaxies, of course, but it tended to place them in a more restrained opening scene. The first systems were expected to be present in growing numbers as one moved forward through the first several 100 million years, yet many of them should have been small, faint, and difficult to detect even with advanced instruments. Webb was built to find them, but the expectation was still shaped by gradualism. Better seeing would reveal the hidden population, not a dramatically altered one. Instead, the first deep surveys suggested that ancient fields were more crowded with bright young systems than many pre-launch estimates had preferred. In several analyses, the discrepancy was not subtle. Webb was finding early galaxies in quantities that pressed against the upper edge of expectation, and in some cases went beyond it. The effect was strong enough that astronomers had to ask whether the models had underestimated how efficiently stars formed, how rapidly gas collapsed into luminous systems, or how much the earliest visible galaxies differed from the objects that had been imagined from older data. This is where the emotional shape of the discovery becomes easy to misunderstand. The surprise was not simply that Webb found more galaxies than Hubble. That was almost guaranteed. The surprise was that after accounting for the telescope's greater sensitivity and infrared reach, the early universe still appeared unusually full of detectable structure. Deep field work began to suggest that the infant cosmos had not been waiting quietly for complexity to arrive. It had already begun producing it at a pace that seemed uncomfortably high. The JWST program, one of the major Webb efforts aimed at the deep universe, made this pressure even clearer. By studying regions such as Good South with extraordinary depth, the survey identified many hundreds of candidate galaxies from the first part of cosmic history, including systems from within the first several 100 million years after the Big Bang. In older frameworks, that era was supposed to be visible only through a relatively thin and difficult population of sources. Instead, the catalogues thickened. There were more faint red points to examine, more early candidates to classify, more objects whose light had been shifted into the infrared and was now entering the record in numbers large enough to reshape the statistical background against which theory had been tested. What had seemed like a remote frontier with only scattered landmarks began to resemble a coastline already lined with settlements. That alone would have been enough to force renewed calculation. But the crowding of the sky carried a second implication. Every additional candidate galaxy raised questions not only about existence, but about production. To be seen across such immense distance, a galaxy must emit enough light to survive dilution, redshift, instrumental limits, and the confusion of foreground contamination. A larger than expected population of early detections therefore hints at a larger than expected population of luminous systems, which in turn implies that star formation, gas assembly, or some other source of brightness may have been more efficient in the young universe than the neatest versions of the standard timeline had allowed. The tension did not rest on a single headline claim. It accumulated from repeated encounters with a sky that seemed fuller than anticipated. Still, astronomy is a discipline that lives by caution, and the early Webb results did not escape that caution. Candidate galaxies in the distant universe are often identified first through their colours, because redshift shifts familiar spectral features from one set of wavelengths into another. A very distant galaxy can therefore leave a recognisable pattern in broad filters even before a full spectrum is obtained. This method is powerful, but it is not infallible. Dusty galaxies at lower redshift can sometimes imitate the colours of more distant sources. Active black holes can brighten compact objects and distort first impressions. Gravitational lensing can magnify background galaxies and make them easier to spot than their intrinsic brightness alone would suggest. For all of these reasons, some early claims were always going to be revised, and in fact, revisions came. A number of ancient candidates required follow-up, more precise distance measurements, or reinterpretation once spectra and improved modelling became available. Some objects that first appeared impossibly massive later seemed less extreme. Some populations may have included sources whose light was enhanced by central black holes rather than by stars alone. These refinements matter because they prevent the argument from slipping into false drama. Webb did not prove overnight that the old cosmology had collapsed. But the refinements did not erase the deeper issue either. Even after corrections, a broader pattern remained. The early universe still looked unexpectedly productive. There were still more bright systems than many pre-launch simulations had comfortably predicted. There were still surveys in which the count of ancient galaxies came in high enough to keep the disagreement alive. This is why the crowded deep fields became so important. They moved the discussion away from singular wonder and toward population-level evidence. A single astonishing galaxy can be treated as a challenge at the edge of possibility. A field containing too many early sources begins to feel like a pressure on the baseline itself. It suggests that the difference is not confined to one rare exception, but woven into the general conditions of the young cosmos. In a field that is too full, every new object does two kinds of work. It becomes an individual case to study, and it quietly strengthens the claim that the environment producing such cases may have been fundamentally more efficient than expected. The early universe starts to look less like a place of hesitant assembly, and more like a place already operating at high output. Even the visual character of the images contributed to this change in understanding. Webb's deep views did not present the first billion years as a nearly vacant interval punctuated by isolated sparks. They showed layers of remote structure in which ancient galaxies were not hidden by absence, but by wavelength and faintness. Once the right telescope arrived, the concealed population emerged with a force that changed the mood of the field. Darkness had not meant emptiness, it had meant unread light. And once that light became readable, the early sky no longer supported the older intuition of sparse beginnings quite so comfortably. What had seemed delayed now appeared underway. What had seemed rare now looked common enough to demand a new accounting. Yet abundance by itself does not tell the whole story. A sky can be crowded with primitive objects and still fit a gradual universe. The deeper difficulty begins when those numerous ancient sources are not only present, but bright, structured, and physically more developed than their age seems to allow. That was the next turn in Webb's unfolding challenge. The first surprise was that the distant fields were so full. The harder surprise was the nature of the galaxies filling them. A galaxy does not become difficult for theory merely by existing early. The real strain begins when it appears not only early, but already developed in several ways at once. Brightness is the first clue. In the young universe, there has been less time for gas to collapse, stars to ignite, heavy elements to accumulate, dust to form, and large stellar populations to build up the kind of luminosity that can survive immense distance and still reach a telescope as a clear signal. For that reason, many pre-Webb models expected the earliest observable galaxies to be present but limited, small systems beginning a long climb toward later mass and structure. What Webb keeps returning instead is a pattern of ancient galaxies whose light suggests that the climb may have begun with startling speed. NASA's summary of Webb's first years describes this directly, rather than only a few faint galaxies in cosmic dawn. The telescope has revealed surprisingly bright galaxies within the first few 100 million years after the Big Bang, along with other signs that the universe evolved faster than many astronomers had expected. The significance of that brightness lies in what it implies. A luminous early galaxy is not just an object that happens to be visible. Its light points to underlying production. Enough stars must have formed, or enough gas must have been energized, for the system to stand out across deep time. In some cases, Webb's observations also suggest that these galaxies are not point-like flares dominated by a compact active nucleus, but extended stellar systems already spread across meaningful physical size. That changes the question from whether something unusual briefly lit up the early universe to whether galaxies themselves were assembling, enriching, and radiating far more efficiently than the standard timeline preferred. The problem is not simply one of detection, it is one of pace. JADES-GS-Z 14-0 offers one of the clearest examples of this pressure. NASA reports that the galaxy is observed at a redshift of 14.32, corresponding to less than 300 million years after the Big Bang. More important than the record itself is the character of the object. Webb's observations indicate that it is intrinsically very luminous, and more than 1,600 light-years across, with the light coming mainly from young stars rather than being dominated by emission around a growing supermassive black hole. The amount of starlight suggests a galaxy already containing several hundreds of millions of solar masses in stars. NASA's accompanying description of the object frames the central puzzle with unusual bluntness. How can nature make a galaxy so bright, massive, and large in less than 300 million years? That question becomes heavier once chemical maturity enters the picture. In the same NASA account, the galaxy is described as showing evidence of oxygen through strong ionized gas emission. Oxygen is not primordial. It is forged inside stars and dispersed after those stars evolve and die. Its presence so early implies that more than one generation of very massive stars may already have lived, ended, and enriched the surrounding gas before the galaxy is seen. Dust also appears to play a role in reddening the light, another sign that the environment is not chemically pristine in the simple sense once favoured for such an early epoch. These details matter because they compress multiple stages of galactic history into a very short span. First stars must form. Some of them must live quickly and die. Their products must mix into gas. New stars must then form in an already altered medium. A galaxy showing that change so soon after the beginning is not merely present ahead of schedule, it is layered ahead of schedule. The same tension appears in broader survey language from NASA. Webb's science summaries note not only bright galaxies within 300 million years, but also an infant Milky Way type galaxy at roughly 600 million years. Galaxies that had already stopped forming stars within the first billion years, and even modern-looking grand design spirals by around 1.5 billion years. Each of these cases points to a different form of maturity. A Milky Way type system suggests organization at a scale that sounds more familiar from the later universe. A galaxy that has already quenched its star formation implies that it not only built itself quickly, but moved into a quieter state remarkably early. A spiral with developed structure suggests that ordered disks and patterns may emerge sooner than expected under the right conditions. None of these findings alone invalidates the standard cosmological model. Together, however, they shift the emotional center of the evidence. The early universe begins to look less like a prolonged assembly yard and more like a period of accelerated experimentation, where mass, light, chemistry, and structure advance in parallel. One response to this has been to ask whether the observations are being interpreted too dramatically. Could some of these galaxies only look extreme because their stellar populations are unusually efficient at producing light? Could active black holes add brightness that makes the host system seem more massive than they truly are? Could dust, geometry, lensing, or modelling assumptions distort the first estimates? These are not evasions. They are exactly the questions astronomy should ask. Webb's results have led to many revisions already, with some early candidates proving less extraordinary after follow-up measurements, but the deeper issue has survived that process of correction. NASA's more recent reporting on the galaxy MOM-Z14 notes that it belongs to a growing group of surprisingly bright galaxies in the early universe. with the research team describing a population far more common than theoretical studies had predicted before Webb launched. The implication is not that every headline interpretation from the first months was right. It is that even after the field became more careful, the broader mismatch between early observations and pre-launch expectations did not disappear. MOM-Z14 sharpens the picture in another way. Observed only 280 million years after the Big Bang, it appears not merely bright but chemically unusual. NASA notes signs of strong nitrogen enrichment, which is difficult to explain through ordinary generations of stars in such a short interval. One possibility raised in the report is that the dense environment of the early universe may have favoured supermassive stars capable of producing far more nitrogen than stars commonly seen nearby. Whether that idea proves correct or not, the fact that it must be entertained at all shows how far the discussion has moved. Webb is not only asking whether the first galaxies formed sooner, it is forcing astronomy to ask whether the physical conditions of early star formation, chemical enrichment, and feedback may have been different enough to require new assumptions inside the existing framework. This is where the pressure on lambda CDM becomes subtle. The large-scale structure of the model may still work. The Big Bang remains overwhelmingly supported. Dark matter remains central to how structure is thought to grow, yet the timetable attached to visible galaxy maturity may be too conservative, or the recipes used to convert dark matter halos, gas inflow, cooling, turbulence, and stellar feedback into real luminous systems may be incomplete. A blueprint can preserve the outline of a machine while underestimating the efficiency of its engine. That is the shape of the problem now emerging. Webb has not simply found galaxies earlier than expected. It has found signs that at least some of them were already busy becoming something substantial. The result is a shift in how cosmic dawn is imagined. It no longer settles easily into the old sequence of small, faint, chemically simple precursors waiting patiently for billions of years to become grand systems. Instead, the first few 100 million years begin to look crowded with fast processes, intense star formation, early enrichment, dust production, structural growth, and perhaps black hole activity unfolding together. In that environment, brightness is not a surface trait. It is evidence of work already done. Every ancient galaxy luminous enough to reach Webb from that distance carries with it a quiet accounting of how much assembly must have preceded the moment of observation, and increasingly, that accounting comes back higher than expected. What unsettles the older narrative is not merely that the early universe contains galaxies, it is that some of those galaxies already seem to have lived through more history than their age should comfortably allow. The next step in that tension lies with the most severe cases of all, the system so unexpectedly massive that astronomers gave them a name reflecting the scale of the problem they represent. Redness becomes a problem only after it is interpreted. In Webb's deep fields, some of the earliest bright galaxies do not appear blue and raw in the way a simple picture of cosmic youth might encourage. They appear red, compact, and in several cases surprisingly substantial, as though a long period of growth has already taken place behind the light now reaching the telescope. The nickname red monsters emerged because these systems seemed too large, too mature, or too heavily built for the short interval available to them. They earn the name because their estimated stellar masses, inferred from the light they emit, rise into a range that should have taken far longer to assemble if the usual timetable of galaxy formation is even roughly correct. In the standard gradual picture, the first several 100 million years after the Big Bang should contain the earliest successful galactic construction, but not many systems already approaching the stellar scale of much later galaxies. Matter still has to fall into dark matter halos, gas still has to cool, stars still have to form in large enough numbers to create strong infrared light. Then those stars must continue forming or merging over time if a galaxy is to become truly massive. The red monsters seem to compress the entire sequence into a span so short that the compression itself becomes the central fact. This is why the problem they represent is not merely observational surprise, it is a timing problem written into starlight. The concern begins with mass estimates. Its mass has to be inferred from brightness, colour, size, spectrum, and models of how different stellar populations produce light over time. That process always carries uncertainty. A galaxy that looks extremely massive may turn out, after better analysis, to contain fewer stars than first believed. Dust can redden light and make a galaxy appear older or heavier than it truly is. A central black hole, if actively feeding, can brighten the core and distort the apparent contribution from stars alone. Yet even once those cautions are admitted, the early Webb data still left astronomers facing a population of ancient galaxies whose inferred masses seemed uncomfortably high. Some estimates placed them in a range comparable to substantial modern systems, but at an epoch when the universe was still in its first billion years. A red monster is not simply an interesting galaxy. It is a galaxy whose existence, if the measurements are close to right, forces a hard question about how structure could have advanced so far so fast. The redness itself is part of the puzzle, because it can be read in more than one way. In nearby galaxies, redder light often suggests older stellar populations, more dust, or both. In the deep universe, where redshift already shifts all emitted light toward longer wavelengths, the interpretation becomes more delicate. A very distant galaxy can appear red because its light has travelled across expanding space. But once redshift is accounted for, some early systems still seem to possess internal properties that imply either significant dust content, large accumulated stellar mass, or an evolved population of stars that has already moved beyond the youngest and brightest phase. None of those possibilities fits easily with a universe that is only a few 100 million years into galaxy formation. Dust is especially revealing. Dust does not emerge at the beginning. It is made from heavier elements produced in stars and dispersed into surrounding space. A dusty galaxy therefore implies prior stellar generations, death, enrichment, and recycling. In a very young cosmic setting, that whole chain has to happen on an accelerated schedule. The red monsters seem to suggest exactly that kind of acceleration. They look less like first drafts and more like systems that have already passed through several rounds of internal history. What makes the problem more severe is that mass in cosmology is never only about one object. If a single early galaxy appeared impossibly large, the first response would be to question the estimate. If several such systems appear across multiple deep fields, the issue broadens. Their existence starts to imply that the pathways producing them may not be rare accidents. Perhaps the earliest dark matter halos gathered gas more efficiently than expected. Perhaps star formation in dense primordial environments was far more intense. Perhaps feedback from young stars did not suppress assembly as strongly as assumed. Perhaps early black holes and starbursts coexisted in ways that alter how light is interpreted. Each of these ideas tries to reduce the tension without abandoning the overall structure of cosmology, but the need for so many rescue paths reveals how narrow the older timetable has become under Webb's gaze. The red monsters matter because they expose the point where flexibility in the model begins to look like strain. A useful way to grasp the difficulty is to separate luminosity from assembly. A galaxy can be bright for a short time if star formation becomes intense enough, and young massive stars are extraordinarily luminous. But to remain bright in a way that also suggests high stellar mass, a galaxy needs not just a flare of activity, but a substantial underlying population of stars. That means large amounts of gas must already have been converted into long-lived structure. A brief burst helps. It does not solve everything. The red monsters appear to require both high output and prior build-up. In that combination lies the real discomfort. It is one thing for the early universe to light up. It is another for it to have already built so much of the machinery that produces the light. The analogy sometimes used by astronomers is revealing because it sounds almost absurd. It is like finding a very small child with the weight and size of a mature adult. The problem is not that growth has occurred. The problem is the rate at which growth seems to have happened. Under ordinary expectations, there has not been enough time for the process to pass through all the needed stages. If an early galaxy contains a vast stellar population, then huge quantities of gas must have collapsed, cooled, fragmented, and formed stars at extraordinary speed. Some of those stars must then have lived long enough to alter the composition of the system. The more each of those conditions is considered in sequence, the harder the timeline becomes to defend without revision. This does not mean the measurements are beyond challenge. In fact, much of the ongoing work around these galaxies is an effort to reduce the masses, refine the distances, and test whether active galactic nuclei or hidden line emission are inflating the estimates. Webb itself has already taught that some extreme early claims need refinement, but even a softened red monster remains important. A galaxy does not need to keep its most dramatic first estimate to remain theoretically uncomfortable. If several systems turn out to be somewhat less massive than they initially feared, yet still more mature and substantial than many models expected before Webb, then the pressure remains, only in a more measured form. The issue is not whether the most alarming numbers survive intact. The issue is whether the early universe repeatedly produces galaxies that sit at the edge of or beyond the efficient limits built into current models of formation. There is also a deeper conceptual reason these galaxies feel so unsettling. Modern cosmology is strong on large-scale evolution. It describes expansion, background radiation, and the growth of structure across immense volumes with impressive success. But the transformation from invisible dark matter scaffolding into real luminous galaxies depends on messy local physics as well as grand cosmic rules. Gas cooling, turbulence, feedback, metal enrichment, dust formation, and black hole growth all operate on scales far smaller than the universe itself. Yet they determine how quickly a halo becomes a visible galaxy. The red monsters occupy the boundary between those two levels of understanding. They may not be telling astronomers that the universe began differently. They may be telling them that visible matter learned to organize itself under early conditions much faster than the standard recipes allowed. That is a subtler disturbance, but not a minor one. These galaxies do not merely add another strange class of object to the Webb era. They challenge the tempo of the first billion years. They imply that by the time the universe is still wrapped in what should be its formative youth, some of its galaxies may already have crossed into a level of maturity usually reserved for later chapters. If that is true, then cosmic dawn was not a thin prelude waiting patiently for complexity. It was an interval of rapid accumulation, early enrichment, and large-scale construction, moving at a pace that now seems difficult to reconcile with the calm, sequential version of events once thought secure. The question is no longer only whether early galaxies existed in abundance. The harder question is what hidden conditions allowed some of them to become so unexpectedly heavy before cosmic time had barely begun to open. The strongest clue that the early universe may have been busier than expected does not come from shape alone or even from brightness. It comes from chemistry. A very distant galaxy can look surprisingly large. It can look unexpectedly luminous. It can appear redder or dustier than the simplest models prefer. But when its light carries the signatures of elements that only stars can make, the argument changes. The question is no longer just how a galaxy became visible so quickly. The question becomes what had already happened inside it before that light ever began its journey. Hydrogen and helium emerge from the hot beginning of the universe itself. They belong to the first inventory. Carbon, oxygen, nitrogen, and the other heavier elements do not. They are forged later, inside stars, through fusion and through the violent deaths of the most massive ones. Their presence in a galaxy therefore means that some stellar history has already unfolded. Stars must have formed. At least some of them must have lived fast enough to die young. Their interiors must have manufactured new elements. Those elements must then have escaped into surrounding gas, mixed into the environment, and become part of the material from which later stars and dust could form. In a mature galaxy, this is expected. In a galaxy seen from the first few 100 million years of cosmic time, it becomes a far more serious claim. Webb's distant galaxies are beginning to make exactly that claim. One of the clearest cases comes from the record-setting source known as JADES-GS-Z14-0, observed from less than 300 million years after the Big Bang. Its importance does not rest only on its distance, it rests on what that distance leaves available. At such an early epoch, the universe has had very little time to build complexity. Yet the light from this galaxy does not suggest a pristine object only just beginning to shine. It suggests a place where stars have already been active enough to alter the surrounding matter. The detection of oxygen in such an early system is especially revealing, because oxygen is one of the classic products of stellar life cycles. It is made in stars and distributed into space when massive stars end their lives. Its appearance means that at least one earlier generation of stars must have lived and died before the galaxy is being seen. The galaxy therefore arrives not as a beginning, but as a result. Behind the observed light there seems to be an unseen interval of prior work, compressed into a span that cosmology once imagined as only the first opening movement of galactic history. This is why chemical enrichment matters more than a simple distance record. A remote galaxy can be astonishing and still fit within an expanded version of the usual story. A chemically enriched remote galaxy forces the story to start earlier than expected. In the calm sequence once preferred, the first stars ignite, then over time they enrich the gas around them, then later generations inherit that altered chemistry. Webb is increasingly finding hints that some of this sequence may have been underway almost as soon as galaxies became observable at all. The first visible systems may not be first in any clean sense. They may already be second or third generation environments, containing the after effects of stellar births and deaths that happened even earlier, in sources too faint, too brief, or too primitive for present instruments to isolate directly. In that case, the early universe shown by Webb is not the beginning of structure, but the aftermath of beginnings that had already passed. Dust deepens that impression. Dust is easy to describe and difficult to dismiss. It is made from heavier elements, often in the outflows of dying stars and in later recycling through interstellar clouds. A dusty early galaxy implies that enrichment has gone beyond a trace event. It suggests that stellar processing has already started to alter how light moves through the system, dimming and reddening it in ways that belong to a chemically active environment, rather than to untouched primordial gas. When Webb sees signs that some of its earliest galaxies are not as blue as a purely young and unpolluted stellar population might suggest, the consequence is quiet but significant. The galaxy may already contain the products of prior stellar generations, and that in turn means that the hidden history behind the visible object is longer and more layered than its age seems to allow. Even a small amount of dust at such an early time carries the weight of previous cycles. It hints that the universe learned to recycle matter far faster than the older gradual picture had assumed. This is where the idea of the first stars becomes especially important. Astronomers have long expected that the earlier stellar generation was unlike most stars seen today. In the pristine gas of the young universe, with almost no heavy elements present, the first stars may have formed under different conditions, perhaps growing unusually massive and living very short lives. These hypothetical first stars often discussed as population 3 stars, remain difficult to observe directly. They may have burned brightly and vanished quickly, leaving only indirect evidence in the chemical fingerprints of later systems. Webb's enriched early galaxies raise the possibility that their traces are beginning to show, not through direct portraits of those first stars themselves, but through the oxygen, nitrogen, dust, and altered starlight left behind in the galaxies that follow them. If that is true, then the earliest visible galaxies are standing on top of an invisible stellar prehistory, and the gap between the first ignition of stars and the emergence of substantial galaxies may be much shorter than expected. Another distant system, MOM-Z14, pushes this reasoning even further by suggesting unusual nitrogen enrichment at an age when standard stellar generations should barely have had time to begin such work. Nitrogen is not impossible to explain, but the amount inferred in some of these observations appears difficult to produce through ordinary star formation histories compressed into such a brief span. One response is to suggest that the first stellar environments may have favoured objects unlike those common in the nearby universe, perhaps even supermassive stars capable of unusual chemical yields. That remains uncertain, but the fact that such possibilities must be entertained shows what Webb has done to the discussion. The telescope is no longer merely measuring when galaxies became visible. It is probing what kinds of stars may have existed before those galaxies reached the state now being observed. The debate begins to move beneath the galaxies themselves, down into the nature of the earliest engines of enrichment. Yet chemical evidence, like all evidence from the deep universe, has to be handled with care. Spectra are delicate. Interpretations depend on line strengths, redshift solutions, models of gas conditions, and assumptions about how stars of different masses contribute to the observed light. There is always room for revision, and the field is still young enough that some of today's most provocative interpretations may soften with time. But uncertainty does not remove the force of the current pattern. The broader issue remains that multiple early galaxies now seem to contain signs of material that should have required prior stellar activity. Even if individual estimates change, the direction of the evidence is difficult to ignore. Webb keeps finding that the young universe was not chemically blank. It had already begun to remember itself. That memory is carried in atoms forged inside stars no longer present, in dust that can only exist after processing, and in gas clouds whose composition implies an earlier round of light before the light now being studied. In that sense, the telescope is beginning to reveal not only early galaxies, but ancestral layers within them. The visible object becomes a kind of archive. Its starlight records active stars in the present moment of observation. Its chemistry records stars that are already gone. Its dust records cycles of creation and dispersal that should have required time the universe barely seems to possess. This layered quality makes the early cosmos feel less like a fresh beginning, and more like a world already carrying inheritance. The first galaxies now visible to Webb may not be newborn structures at all. They may be descendants, shaped by events that took place in an even darker interval behind them. That possibility changes the emotional contour of cosmic dawn. Instead of a simple rise from emptiness into light, the opening of the universe begins to look recursive. Light appears, disappears, and leaves transformed matter behind for the next light to inherit. What Webb detects is only the part that survives long enough and grows large enough to be seen. Beneath it may lie a missing generation of early stars whose existence is written indirectly into enriched gas and reddened starlight. The universe, in that view, becomes more hurried and more layered at once. Its first visible galaxies are not first drafts. They are already edited by prior fire. The beginning, once imagined as a sparse and chemically simple scene, starts to look like the aftermath of earlier, faster, and largely hidden episodes of creation. And that means the true challenge posed by Webb is not merely that galaxies arrived early. It is that history itself may have started accumulating inside them before astronomy expected there to be enough time for history at all. The little red dots are unsettling for a different reason than the early giant galaxies. A massive galaxy can be imagined, however uncomfortably, as an extreme outcome of rapid assembly. The little red dots resist even that kind of uneasy acceptance because they do not present themselves as scaled-down versions of anything familiar. They are small on the sky, strikingly red in Webb's infrared images, unexpectedly common at high redshift, and difficult to place inside the categories that astronomers normally use to sort the distant universe. NASA describes them as numerous red objects that appear small on the sky. First revealed by Webb less than 6 months after science operations began, and notes that researchers remain perplexed by their nature, by the reason for their colours, and by what they might be telling astronomy about the early universe. In one of the larger samples assembled so far, nearly all of them come from within the first 1.5 billion years after the Big Bang. What gives these objects their peculiar force is not simply that they are distant. The early universe contains many distant things. It is that they combine several awkward properties at once. They are compact, with a morphology that makes them look almost point-like or only slightly extended in Webb images. They are red in the rest frame optical sense used to identify them, yet not in the same way that an ordinary dusty low redshift interloper would be, and they appear over a broad but still distinctly early redshift range, with one large Webb sample identifying 341 of them across surveys including CEERS, PRIMER, JADES, UNCOVER, and NGDEEP. That study characterizes them as compact sources with red rest frame optical colors and blue rest frame ultraviolet colors, a combination that already hints that their light is not being produced by an ordinary stellar population alone. Their abundance adds another layer of difficulty. In the NASA summary of the large sample compiled from public Webb fields, the population rises into prominence around 600 million years after the Big Bang, and then declines rapidly by roughly 1.5 billion years after the Big Bang. That pattern matters because it makes the little red dots look like a phase, not merely a handful of oddities. They seem to belong to a particular interval in cosmic history, appearing in large numbers when galaxies and black holes are still in the act of early assembly, and then fading from the census as the universe moves into later eras. A rare anomaly can be set aside as an edge case. A population with a recognizable time window begins to look like a missing chapter in the normal picture of growth. One obvious interpretation is that these objects are telling astronomers about black holes. The case for that idea does not rest on appearance alone. NASA reports that spectroscopic data from the Rubies survey found evidence in about 70% of the studied targets for rapidly orbiting gas at around 1,000 kilometers per second, a signature associated with accretion disks around supermassive black holes. Independent Webb analyses have also found fast-moving hydrogen gas in some little red dots, again pointing toward accretion rather than pure starlight as part of the explanation. The appeal of this interpretation is strong because it helps connect several mysteries at once. If at least many little red dots are active galactic nuclei wrapped in gas and dust, then their strange redness, compact appearance, and unexpected brightness may be telling astronomers that Webb is catching an obscured phase of early black hole growth that earlier observatories could not isolate. Yet even the black hole explanation does not make the problem disappear. It changes the problem. If the little red dots are accreting black holes, then the early universe was building black holes quickly enough and hiding them effectively enough to produce a widespread population of compact red sources in its first billion years. That is already a significant demand on theory, because the formation of heavy black hole seeds and their rapid growth remain active questions in cosmology. ESA's report on CANUCS-LRD-Z8, 6, a little red dot observed less than 600 million years after the Big Bang, describes clear spectral evidence for an accreting supermassive black hole and notes that the black hole appears overmassive relative to the galaxy's stellar mass. In that system, the black hole seems to be growing faster than the host galaxy itself, which hints that some early galaxies may have passed through a stage where central black hole growth outpaced the assembly of their stellar bodies. That possibility is profound because it would reverse a comfortable intuition about how galaxies mature. In the nearby universe, the masses of central black holes and their host galaxies often show broad relationships, as though the two forms of growth have been negotiating over cosmic time. The little red dots suggest that in the early universe this balance may have been temporarily broken. Some systems may have concentrated energy and inflow into the center first, building black holes in dense obscured environments before the visible stellar component caught up. If so, these objects are not only mysterious galaxies, they may be witnessing an early pathway by which the universe assembled the massive black holes that later power quasars. NASA's release on the little red dots frames the issue in exactly this way, as a potential peek into a previously hidden era of obscured black hole growth. Even so, the matter is not settled. Researchers continue to debate how much of the light in little red dots comes from stars and how much comes from gas around black holes. NASA's reporting explicitly stresses that there are always multiple ways to explain the confounding properties of these sources, and that the field remains an exchange between models and observations rather than a solved classification problem. The same caution appears in theoretical work. The large sample paper argues that the sources are likely heavily reddened active galactic nuclei tracing a previously hidden phase of dust-obscured black hole growth, but that wording itself remains probabilistic rather than final. Other current papers explore whether the spectra can be explained by young low-mass active nuclei embedded in dense ionized cocoons, by direct collapse black holes, or by even more exotic progenitors tied to supermassive stars or quasi-star-like stages. Those ideas do not all carry the same evidential weight, but their very number reveals how incomplete the interpretive framework still is. There is also an instructive irony here. Some of the earliest alarm over Webb's apparently overmassive ancient galaxies has softened as astronomers recognized that light from little red dots and similar compact active systems can make certain sources look more stellar-rich than they really are. NASA has highlighted this point directly, noting that evidence for black hole accretion in little red dots supports the conclusion that at least some of the early compact red objects are probably not as massive in stars as the first interpretation suggested. In other words, the little red dots may solve one problem while deepening another. They may reduce the claim that the early universe produced huge stellar systems impossibly fast, yet at the same time strengthen the claim that it produced rapidly growing and sometimes overmassive black holes with unexpected efficiency. That trade matters because it clarifies what Webb is really doing to the early universe story. The telescope is not simply accumulating curiosities, it is forcing astronomers to disentangle mechanisms that older observations blurred together. A bright compact red source in the early universe could once be imagined mostly as a young galaxy, with a large stellar mass. Webb's spectroscopy now makes it possible to ask whether some of that light is instead passing through, or being generated by a buried accretion structure around a black hole. The result is more precision, but not less mystery. The little red dots remain difficult because they sit at the crossing point of several unresolved histories: the birth of galaxies, the birth of massive black holes, the role of dust and dense gas in the young cosmos, and the question of whether early central engines grew from ordinary stellar remnants or from much heavier seeds. Their compactness adds one last layer of tension. If much of their luminosity really comes from tiny central regions, then Webb may be seeing environments where the universe has packed enormous power into very small scales very early on. If instead part of the population includes unfamiliar stellar structures, then the problem shifts again, toward physical conditions in the first galaxies that allowed unusual objects to form and shine. Either path is difficult. The black hole route asks how such seeds formed and fed so early. The stellar route asks what kind of short-lived objects could mimic the observed spectra and why they appear in a distinct redshift window. For now, the evidence leans strongly toward black hole activity in many cases, but not yet toward a single complete explanation for the whole class. That is what makes the little red dots so important. They are not merely strange points of light. They are a population that seems to emerge suddenly, flourish during a narrow and formative interval, and then recede, leaving behind the possibility that Webb has opened onto an early phase of cosmic development that had been almost entirely missed. In a calmer universe, they would be classified and absorbed. In the universe Webb is revealing, they remain suspended between interpretation and revision. They may be the first clear sign of widespread hidden black hole growth. They may also be a reminder that the young cosmos still contains categories astronomy has not yet learned to name with confidence. What they do not resemble is a minor detail. They sit too close to the origin of galaxies, too close to the growth of black holes, and too densely within the first billion years to be treated as decoration. They narrow the problem rather than solve it. Somewhere behind their red light lies a mechanism the standard story did not fully anticipate, and until that mechanism is understood, the early universe remains more inventive than its models have comfortably allowed. Before the early universe had finished clearing its own hydrogen fog, it was already becoming complicated in motion as well as in light. The older picture of cosmic dawn allowed for the first stars and galaxies to appear gradually, like isolated structures waking one by one inside a mostly opaque background. But Webb keeps uncovering signs that isolation may be the wrong way to imagine those first visible systems. They do not always behave like lonely pioneers scattered across empty space. Increasingly, they look like participants in a crowded and interactive environment, one in which radiation, gravity, gas flows, and early assembly are already influencing one another on surprisingly large scales. That shift matters because a universe can contain early galaxies and still remain broadly calm in its developmental rhythm. The deeper disturbance begins when those galaxies seem to be shaping their surroundings, merging into larger structures and altering the state of intergalactic space much sooner than expected. In that case, cosmic dawn stops looking like a thin prelude and starts to look like an era already dense with consequences. One reason this matters is that the early universe is not only a matter of when galaxies first became visible, it is also a matter of what filled the space between them. After the Big Bang and the cooling that allowed neutral hydrogen to form, much of intergalactic space was veiled by that hydrogen in a state that blocked energetic ultraviolet light. This was not darkness in the ordinary sense. It was a kind of cosmic opacity. Young galaxies could form within it, but their most revealing radiation would be absorbed and scattered until enough stars and galaxies produced enough ionizing light to transform the gas around them. This long transition is known as reionization, and for many years it was imagined as a slow, uneven clearing of the fog. Webb is now showing that the process may have been more active, more locally dramatic, and in some places farther along than expected at very early times. NASA reports that JWST 13-1 is observed just 330 million years after the Big Bang, yet it shows bright Lyman alpha emission from hydrogen, a signal astronomers did not expect to see so clearly because the surrounding neutral hydrogen should still have blocked it at that stage. The implication is that the galaxy either sits inside a surprisingly large transparent bubble, or has somehow contributed to creating one. which means that the surrounding medium was already being transformed in a way theory had not comfortably predicted for such an early epoch. That one result would already be significant, but its importance grows because it does not stand alone. NASA's reionization results from Webb show that comparatively small galaxies were capable of clearing immense regions of gas around themselves, producing transparent bubbles vastly larger than the galaxies at their centers. Over time, those bubbles expanded and merged, eventually making the universe broadly transparent to energetic light. This is a very different visual and physical image from the older intuition of timid, isolated early systems. It suggests that even modest galaxies in the young universe were not merely passive markers of time. They were agents changing the state of space around them, cutting holes in the fog and helping to restructure the visibility of the cosmos itself. A young universe in which such bubbles are already present and beginning to overlap is not only lit, it is undergoing environmental change on large scales. Once that environmental activity is admitted, mergers and interactions begin to feel less surprising, though no less important. The standard framework has always expected small galaxies to merge into larger ones. That is a foundational part of hierarchical growth. NASA's own explanation of Webb's early universe science notes that the telescope may help reveal how small galaxies in the early universe merge to form larger galaxies. But the pace matters. A process that is expected in general can still become uncomfortable if the evidence suggests it is already well underway when the universe is only a few 100 million years old. Webb's deep fields and the reference material associated with this project point toward just such a possibility, with compact groupings and interacting systems appearing earlier than the gentlest versions of the old timeline preferred in that setting. Mergers are not the later consolidation of an already mature universe. They are part of the first visible rush of assembly itself. That changes the emotional structure of cosmic dawn. If galaxies are already colliding, tugging on one another, or gathering into dense association so early, then the first billion years cannot be treated as a long quiet build-up toward later complexity. Complexity is already present in the relationships between systems, not just in the internal properties of one galaxy at a time. Gravity is already organizing neighborhoods, not merely isolated islands. Radiation is already altering the medium between galaxies, not merely illuminating stars within them. The early universe begins to resemble a place where multiple forms of structure formation are unfolding in parallel stars within galaxies, galaxies within groups, and ionized cavities within the hydrogen sea between them. Each layer of activity reinforces the others. More stars mean more ionizing light. More interactions can mean more inflow of gas and more rapid star formation. More cleared bubbles allow certain kinds of radiation to travel farther, changing what becomes observable and perhaps influencing nearby regions. The universe does not look leisurely in this picture. It looks coupled. Even the phrase early universe begins to lose some of its simplicity. Early once implied primitive, sparse, and only partly assembled. Webb's results force a more careful distinction. A region can be early in age and still dynamically rich. It can exist near the beginning of cosmic history and already contain turbulence, feedback, clustering, and the first signs of environmental engineering by galaxies themselves. This does not mean that the whole universe was uniformly advanced. Reionization was patchy, and much remained opaque for a long time, but patchiness itself becomes part of the story. Some regions appear to race ahead, building stars quickly enough and emitting enough energetic radiation to carve out local transparency, while other regions remain murky. The first billion years then begin to look less like a single universal stage and more like a landscape of uneven development, where some pockets of the cosmos mature far ahead of the average. That unevenness makes the timeline harder to narrate in a straight line. There is another important consequence here. Once the young universe becomes visibly interactive, the distinction between local surprises and global model pressure begins to narrow. An unusually bright galaxy can be treated as a local puzzle. A chemically enriched object can still be discussed as a special case. But a cosmos in which early galaxies are numerous, rapidly assembling, already affecting the surrounding intergalactic medium, and perhaps merging into denser structures begins to suggest that the issue is not confined to a handful of extraordinary objects. The issue may lie in the general efficiency of early structure formation. Webb does not merely find galaxies too soon. It finds a universe in which several connected processes seem to have accelerated together. That combination is much harder to absorb because it points toward the timing rules themselves. Perhaps gas cooled more effectively in early halos. Perhaps the first stellar populations produced ionizing radiation more efficiently than expected. Perhaps feedback behaved differently in primordial conditions. Perhaps the first dense regions of the cosmic web became active earlier and more unevenly than older simulations favoured. None of these revisions requires abandoning the Big Bang or even discarding the broad outline of lambda CDM. But together they imply that the visible universe may have moved from first light to environmental transformation with startling speed. The old sequence survives, but its tempo begins to feel wrong. This is why the early mergers and ionized bubbles matter so much. They are not decorative anomalies placed around the edges of Webb's main discoveries. They are evidence that the young cosmos was already doing several difficult things at once. It was making stars, it was enriching gas, it was growing black holes in at least some compact systems, it was assembling galaxies into more massive structures, and it was changing the transparency of intergalactic space. Once all of those processes are placed in the same era, the phrase chaotic early universe no longer sounds like exaggeration. It sounds like a practical description of a cosmos that reached dynamical complexity faster than expected. The result is not simply a more crowded beginning. It is a beginning in which cause and consequence are already feeding back into one another. Galaxies are no longer just products of cosmic history. They are already becoming engines that modify that history around them. That is the deeper threshold reached in Webb's early universe. The first visible galaxies do not merely appear. They interact, radiate, alter, and gather, leaving behind a picture of cosmic dawn that is not slow and sparse, but active enough to make the broader timing of the universe feel less settled than it once did. And once the timing itself comes into question, the tension no longer belongs only to early galaxies. It begins to press against the larger framework used to describe the expansion history of the universe as a whole. There is another way in which the universe now seems uneasy with the story told about it, and this one does not begin with distant galaxies at all. It begins with a number. The Hubble constant is the present expansion rate of the universe, a measure of how quickly cosmic distances increase on the larger scales. In principle, this number should be accessible in two different ways that ultimately agree. One can measure it directly in the nearby universe by building a distance ladder from well-understood objects such as Cepheid variable stars and Type Ia supernovae. Or one can infer it from the very young universe by studying the cosmic microwave background, fitting those early conditions with the standard cosmological model, and projecting forward to the present day. For a long time, the expectation was simple. These two routes might differ slightly because of uncertainty, but as the data improved, they should converge on the same answer. Instead, the better the measurements became, the clearer the mismatch grew. NASA's Hubble mission explains the basic divide. Directly local distance ladder measurements yield a higher present expansion rate, while the value inferred from the cosmic microwave background and the standard model is lower, leaving what astronomers now call the Hubble tension. The early universe side of the tension is anchored in the afterglow of the Big Bang. ESA's Planck material describes how the pattern of the cosmic microwave background can be used, together with the standard cosmological model, to predict what the Hubble constant should be today. giving a value around 67 and a fraction kilometers per second per megaparsec. On the local side, NASA's Hubble pages summarize values in the low to mid-70s from distance ladder work using Cepheids and supernovae. The numerical gap is not enormous in everyday terms, but in precision cosmology, it is large enough to matter because both methods have become impressively refined. The tension is therefore not a casual disagreement between rough estimates. It is a conflict between two highly developed descriptions of the same universe, one rooted in its early conditions and one in its nearby present. For years, one possible way out was to suspect that the local ladder still contained subtle observational errors. Cepheid stars often lie in crowded regions of their host galaxies, and when stars sit too close together in an image, the light of neighbours can contaminate the measured brightness of the target. Because distance estimates depend on brightness, even a small systematic effect could shift the inferred expansion rate. This possibility mattered enough that it became one of the major reasons to bring Webb into the problem. Its infrared vision is sharper in precisely the way needed to isolate Cepheids from surrounding stars and to reduce the confusion caused by dust and crowding. NASA's Webb team described this motivation clearly in the announcement of the first relevant results Webb was being used to scrutinize and refine some of the strongest observational evidence behind the tension by improving the precision of local measurements and checking whether Hubble had somehow been biased by the environments in which those standard candles were observed. The result was not the relief many cosmologists had hoped for. Webb did not reveal that Hubble had been badly fooled. It confirmed that Hubble had essentially been right. NASA states that Webb's sharper infrared vision allowed Cepheid targets to be more clearly isolated from surrounding stars, and that the new data confirmed the accuracy of 3 decades of Hubble observations used to establish the lower rungs of the cosmic distance ladder. ESA summarized the same outcome even more bluntly, noting that Webb raised lingering doubt about Hubble's measurements and that the tension remained a nagging puzzle. In other words, one of the cleanest suspected sources of error on the local side weakened rather than strengthened under closer inspection. That matters for more than one reason. First, it means the disagreement is harder to dismiss as a technical artifact of older instruments. Second, it changes the emotional character of the problem. A tension caused by poor photometry is annoying but limited. A tension that survives a major cross-check by a new observatory begins to look more like a property of the universe than a flaw in one telescope's eyesight. NASA and ESA both frame the issue in this direction, with language suggesting that something woven into the fabric of space, or missing from the accepted model, may be responsible if measurement errors continue to fall away. The idea is not that new physics has been proved, it is that the usual refuge of blaming the data grows less comfortable each time a new independent check lands in the same place. Webb's contribution did not stop with Cepheids. In a later result, NASA reported an independent Hubble constant estimate based on a lensed Type 1a supernova, a method that combines gravitational lensing and time delays rather than relying only on the standard local ladder in its usual form. That measurement carried larger uncertainties than the Cepheid-based result, but it still landed in the local universe camp and remained somewhat in tension with values inferred from the young universe. This is important not because it settles the problem, but because it broadens the terrain on which the problem appears. A single method can be doubted. Multiple methods clustering on one side of the divide make the divide more difficult to ignore. At first glance, this may seem separate from Webb's early galaxy discoveries. A disagreement in the expansion rate is not the same thing as overabundant galaxies, little red dots, or unexpectedly rapid chemical enrichment. And it is true that these are not one mystery wearing different clothes. Astronomers do not yet know that they share a single cause, and it would be too strong to claim that Webb's crowded cosmic dawn directly explains the Hubble tension. but the two lines of evidence do press in the same philosophical direction. Both suggest that the cleanest version of the standard story may be leaving something out. On one side, the young universe inferred from the cosmic microwave background and lambda CDM seems to predict a present expansion rate lower than the one measured nearby. On the other side, the directly observed young universe now revealed by Webb often looks more active, more luminous, and in some respects more mature than many pre-launch expectations allowed. These are distinct tensions, but together they reduce confidence in the idea that the visible universe evolves in the simple, well-paced manner once imagined. The likely resolution, if one exists, may not be a dramatic overthrow of cosmology. The Big Bang remains overwhelmingly supported. The cosmic microwave background remains real. Dark matter remains central to the growth of structure in the standard picture. What the Hubble tension suggests instead is that the model may be incomplete in a subtler way. Perhaps there is an ingredient in the early universe that slightly changes the expansion history before recombination. Perhaps dark energy is not as simple as the constant term built into lambda CDM. Perhaps some overlooked systematic still survives in one or more methods, though Webb has made that path narrower. NASA's Hubble and Webb reporting keeps this balance carefully. The discrepancy could signal new physics, but it has not yet revealed exactly what that physics would be. This is where the pressure from Webb becomes especially deep. The telescope has not solved the Hubble tension. It has made it harder to dismiss. By confirming key parts of the local distance ladder, Webb removed one of the more hopeful escape routes, by revealing an early universe full of bright galaxies, rapid enrichment, hidden black hole growth, and unexpectedly active reionization. It also reminded cosmologists that the first billion years may contain processes still not well represented in the simplest standard framework. The tension therefore begins to feel less like an isolated numerical inconvenience, and more like part of a larger pattern in which the universe keeps behaving as though its internal timing is slightly off from what the neatest model prescribes. A universe that expands a little differently than expected is not merely a universe with the wrong number in a table. Expansion sets the pacing for everything else. It influences how matter clumps, how quickly structures emerge, how long different phases of cosmic history last, and how the bridge is built between the nearly uniform early universe and the richly structured one seen today. That is why the Hubble tension has become so unsettling. It is not just another disagreement between teams. It is a mismatch in the conversion between the universe's beginning and its present state. If the mismatch is real, then something in that conversion remains hidden. Webb's great contribution here is not resolution but exposure. It has shown that sharper vision does not necessarily simplify the cosmos. Sometimes it confirms the anomaly. Sometimes it adds a second anomaly beside the first. And when both the early universe and the nearby universe begin to strain in different ways against the same accepted framework, the problem is no longer easy to fence off. The standard model still stands, but it stands under a quieter and more persistent pressure than before, and that pressure leads toward a final realization. The scale newly revealed by Webb is not only the scale of the observable universe, it is the scale of the gap between what can now be seen and what current theory can comfortably explain. There is no wall at the edge of the observable universe. The boundary most often described in cosmology is not a surface where matter stops or where space ends, but a limit set by time, light, and expansion. It marks the greatest distance from which light has had enough time to reach Earth since the universe began, after accounting for the fact that space itself has been stretching while that light travels. That is why the observable universe can have a radius of roughly 46.5 billion light-years, even though the universe is about 13.8 billion years old. The number does not violate anything. It reflects the simple but difficult fact that the cosmos has not stood still during the journey of the light. What matters here is that this vast radius is not the size of the whole universe. It is only the size of the portion that can, in principle, be seen from one location, given the age of cosmic history and the expansion of space. Beyond it, there may be more of the same large-scale structure, more galaxies, more dark matter, more regions with their own local histories, or there may be features of the wider cosmos that current observation cannot yet detect. The limit is therefore not only spatial, it is epistemic. It is a frontier in what can be known by direct observation. This distinction has always been part of cosmology, but the James Webb Space Telescope has made it feel more immediate. By pushing vision closer to the earliest visible eras, Webb has not simply enlarged the catalogue of distant galaxies. It has clarified how quickly the horizon of ignorance rises even as observation improves. Each time the telescope reaches farther back, the expectation might be that the picture should become simpler, because the universe itself is younger. Instead, the opposite has happened. The farther back Webb looks, the more the early cosmos seems to resist the role assigned to it in the older narrative. It is not empty enough, not simple enough, not chemically untouched enough, not dynamically quiet enough, and in that resistance, a larger truth becomes harder to ignore. The terrifying scale revealed by Webb is not only the scale of matter and distance, it is the scale of the mismatch between what human beings can now observe and what their best models can fully explain. The older cosmological story was never crude. It was one of the great intellectual achievements of modern science, a structure built from the cosmic microwave background, the distribution of galaxies, the abundance of the lightest elements, the expansion of space, and the mathematics of general relativity. It remains powerful now, but power is not the same as completeness. A framework can describe the broad architecture of the universe and still leave crucial details unresolved. Webb has exposed those details not as minor loose ends, but as places where the universe appears to have moved faster, organized itself sooner, or hidden its mechanisms more effectively than expected. The problem is not that science has reached a dead end. The problem is that with better instruments, the unknown has not receded in proportion to knowledge. In some regions it has become sharper. That is a different kind of discomfort. It is easier to accept ignorance when the subject is dim and remote. It is harder when the ignorance survives clarity. This is the deeper reason the telescope's findings can feel unsettling, even when they do not destroy the foundations of cosmology. The discomfort does not come from chaos. It comes from structure without full explanation. Webb is not looking into a meaningless fog. It is looking into a past that already contains luminous galaxies, enrichment, hidden central engines, interacting systems, and transformed pockets of intergalactic space. The scene is rich enough to suggest underlying order, but strange enough to imply that the order is not yet correctly understood. In that sense, the true scale of the universe becomes inseparable from the true scale of interpretation. A galaxy seen from the first few 100 million years of cosmic time is not only far away, it is far outside the comfortable range of current intuition. It belongs to a period where every process must happen under compressed conditions, and yet the results keep arriving with the marks of substantial prior history already inside them. That is what gives the Webb era its unusual emotional weight. It reveals not a cosmos collapsing into nonsense, but a cosmos that may be more efficient, more layered, and more inventive than the simplified versions of its history had allowed. There is also a quieter consequence. Human beings do not observe the universe from outside. They observe it from within one galaxy, around one ordinary star, in one local corner of a much larger structure. Every map of the cosmos is therefore drawn from a position that is both privileged and limited. Privileged, because the laws of physics seem readable here, and because light from extraordinary distances can still arrive. Limited, because all those inferences are made from one moving platform inside the thing being studied. The observable universe is centered on the observer in a geometrical sense, not because Earth is special, but because every observer, wherever located, would see a different sphere defined by the same causal rules. This means that even the greatest cosmic surveys are local in a profound way. They do not reveal the universe from nowhere. They reveal the universe as it can be reconstructed from one finite location inside it. Webb intensifies that realization by showing how much can be learned from such a position, and how much still remains hidden. It reaches toward the first light, yet even there it may be seeing only the brighter survivors of earlier events that left no direct image. It reveals massive galaxies, but not necessarily the first invisible steps that made them possible. It detects signs of black hole growth, but not yet the exact origin of the seeds. It sees chemical enrichment, but not the full lives of the earlier stars that produced it. In other words, even the most advanced observations still arrive as fragments. They are real fragments, precise fragments, transformative fragments, but fragments all the same. Cosmology advances by stitching them into a larger story, and Webb has shown that the stitching now needs revision. The terrifying element, then, is not that the universe is infinite, though it may be far larger than the observable part. It is not that the cosmos contains violence, though stars explode and black holes feed and galaxies merge. It is not even that the early universe is stranger than expected, though that too now seems clear. The truly unsettling part is the proportion between the size of the reality and the narrowness of the window through which it must be understood. One telescope extends that window and immediately reveals that previous confidence had rested partly on absence of detail. Another measurement sharpens a long-standing tension in the expansion rate and suggests that something in the accepted model may still be missing. The result is not despair, it is perspective. The universe turns out not to be merely bigger than human scale. It is bigger than the conceptual frames repeatedly built to contain it. Each generation draws a clearer map, and each clearer map reveals new territories of uncertainty around its edges. The movement never really stops. This is not a weakness of science, but one of its most defining strengths. A method that can discover its own incompleteness is more trustworthy than one that pretends to finality. Still, trustworthiness does not remove the feeling produced by the evidence itself. Webb has taken the old dream of seeing the beginning and transformed it into something less reassuring. The beginning, at least the beginning that can now be observed, is not a clean nursery of simple structures waiting quietly to grow. It is already populated by systems with histories, environments with feedback, and objects whose existence hints that important physical pathways were active earlier than expected. The observable universe therefore appears twice enlarged. It is enlarged in space, because the telescope reaches farther into ancient light, and it is enlarged in mystery, because what comes into view does not fit as neatly as hoped. That is the truest sense in which the scale of the universe now feels more severe. It is not only the radius of what can be seen, nor the age written into the furthest photons. It is the realization that even at the threshold of the earliest visible epochs, the cosmos is already ahead of the explanation brought to meet it. The unknown is no longer hidden merely in darkness. It is present inside the light itself, carried across billions of years, waiting in every spectrum, every red point, every overgrown galaxy, every unresolved tension. And that means the final image left by Webb is not of a universe becoming smaller under understanding, but of a universe whose visible face has grown clearer while its deeper logic remains partly beyond reach, immense not only in extent, but in the disciplined, enduring distance between discovery and comprehension. In the end, the James Webb Space Telescope does not make the universe feel smaller by clarifying it. It makes the universe feel more exact, and in becoming more exact, more difficult to contain within old assumptions. The distant galaxies now entering view are not only farther away than earlier generations could study, they are older in the deepest possible sense, carrying forward light from epochs that once seemed almost unreachable. And yet the picture they bring is not one of simplicity. It is a record of rapid construction, hidden histories, chemical inheritance, compact engines, and structures that seem to have begun their work before the accepted timeline feels fully ready for them. That is part of what gives this new era its strange calm weight. The universe is not collapsing into disorder. It is becoming more legible while also becoming less obedient to expectation. The great achievement of cosmology remains intact in outline. There is still a hot beginning, an expanding cosmos, a deep background of ancient light, and a long unfolding of structure across time. But between those broad pillars, the details have become more alive. The first visible chapters are no longer sparse. They are crowded with evidence that history started accumulating early, and that nature may have been more efficient, more layered, and more inventive than the neatest models allowed. Perhaps that is the most lasting effect of Webb's vision. It does not remove wonder by replacing mystery with certainty. It gives mystery firmer edges. It turns ignorance into something more disciplined, more measurable, and therefore more profound. The true scale of the universe may never be felt fully in distance alone. It may be felt most clearly in the widening space between what can now be seen and what still waits to be understood. Patient in the oldest light, unresolved but no longer hidden,